Sì. Allora, buongiorno a tutti, bentornati. Bentornati. Allora, possiamo cominciare con la sessione. Abbiamo deciso, poiché c'è un piccolo ritardo, abbiamo deciso di invertire le due sessioni, quindi prima facciamo la cosiddetta Nobel Session e poi passo il coordinamento a Tommaso Calarco. Quindi cominciamo rapidamente con la Nobel Session. Allora, due degli speaker sono non purtroppo, ma insomma, sono negli Stati Uniti e quindi c'è un'importante differenza di orario e abbiamo registrato ieri il loro intervento, quindi mandiamo l'intervento in differita. Il primo speaker è Tony Leggett, che non ha bisogno di presentazioni, infatti lo faccio in italiano. Ha ricevuto il Premio Nobel per la fisica nel 2003 insieme ad Aberkosow e Ginzburg per contributi pionieristici alla superconduttorità e alla superfluidità. In particolare Tony ha lavorato sulla superfluidità. Uno dei grossissimi passi avanti fatti da Tony Leggett è stato quello di capire come i fenomeni quantistici macroscopici emergono dalla fisica microscopica. Tony è considerato un precursore per questi argomenti da tutta la comunità scientifica. Ieri commentavo proprio con i miei colleghi, con Tommaso, con Dino, con Paolo, che senza le domande che Tony ha fatto 30 anni fa, una buona metà di quello che chiamiamo tecnologie quantistiche oggi semplicemente non sarebbe possibile. Bene, diamo la parola a Tony Leggett e quindi alla registrazione.
Okay.
So, Tony, you know that here we have often tried to connect physics with philosophy, to ask not only... So the presentation will come later. Okay, it's very short, so let me do first the presentation. Now we are very pleased to welcome someone who has been, for many of us, not only a reference in quantum physics, but also a partner in long conversation about what quantum theory really means, and for me personally also a master. Sir Anthony Leggett is a theorist who clarified the role of dissipation and the coherence in macroscopic quantum system, and whose work gave us the language to discuss whether a Josephson circuit can really behave as a quantum object. Many of the debates we had in Naples in the MQC Square years were built on these ideas. Tony, you know that here we have often tried to connect physics and philosophy, to ask not only how to observe macroscopic quantum coherence, but also what that tells us about reality. So we would be very happy if you could leave us a brief message for this timeless Entanglement Day in Pompei, where we are precisely linking quantum theory, memory, and culture. Tony, thank you for being with us again. Thank you very much from my heart. So to you.
Okay.
So a brief message for this timeless Entanglement Day in Pompei.
Okay. Thank you for having me here. Yes, I think, frankly, one of the lessons we should have learned from studying the history of Pompei and the relation between physics and philosophy is that things can come out of the blue and change our perceptions overnight. I'm sure that the inhabitants of Pompei in 79 CE or whatever date it was were going about their daily business thinking that really nothing much is ever going to change in their lives. And then, of course, Vesuvio erupted, and things drastically changed overnight, and our perceptions of their existence in retrospect is probably totally different from what their own was on the day before the volcanic eruption. I think that quite similarly, it might well be that in the relation between physics and philosophy, there's some really basic factor or event that we are missing, which is going to suddenly erupt on us and change our perception overnight. Now, whether that something is going to be a new experiment or a new insight on the theory or something totally different again, I just can't claim to know. As I believe there was a saying which was attributed to the late jazz musician Louis Armstrong, who was asked by a fan where jazz was going, and his reply was, "Man, if I knew where jazz was going, I would be there already." And I think my attitude is the same, that until we actually know in which direction this relationship between physics and philosophy is going, we can't really hope to anticipate it. All we can really do is to tinker around the edges and hope that something useful is going to come out. But as I say, I really think it's going to take some kind of Vesuvio-like catastrophic event to reshake our notions and totally change our perceptions.
Mm-hmm. Hello, Tony. This is Francesco speaking. So happy to see you. So I have a question for you. You were among the very first to clarify how dissipation and coherence affect macroscopic quantum systems. When you look at what people are doing today with superconducting qubits and quantum technology, what strikes you most?
I think what strikes me most is that we can, in fact, and we can actually take quite complicated circuits involving, for example, flux qubits, but the kind of Josephson circuits which are nowadays routinely used in building minimal quantum computers, and we can actually, we do actually have a prescription for working out exactly what it is that dissipation is going to be able to do to those circuits. And at least as far as I know, so far, those predictions have turned out to be in agreement with experiment. This is certainly something I would not have anticipated when I started seriously thinking about these things in the early 80s of the last century. And I think it has been in some ways, very pleasing development, although I should emphasize that it hasn't really got us any closer to solving the fundamental problem of how we get a transition from quantum mechanics to classical mechanics. I mean, I'm continually reading experimental papers in various areas, not just in flux qubits, but also quantum optics and elsewhere, where the authors in the abstract typically say, by doing these studies, we will clarify the transition from the classical to the quantum. Well, I mean, so long as all they are doing in those experiments is to basically get agreement with the standard prescriptions in terms of the Born probability rules and so forth. If that's all they're doing, then I don't think that's really much of an advance. You haven't really clarified very much. There's a big difference with experiments like Michel's and the two Johns, where you've actually shown that you don't simply get the Born rule, you get something a great deal more than that. But for many of these experiments, really, you're simply reaffirming the difficulty. You're not getting any further. But it is very pleasing, nevertheless, that the techniques which were evolved over the last 40 years or so for taking the effects of dissipation into account do, in fact, seem to be working in those experiments.
Hello, Tony. This is Saverio. Very nice to see you again after so many years. You're always the same. Almost no change, I would say. So I have a short question for you. You have often reflected on counterfactuality and interpretation of quantum measurements. We all remember long discussions about the meaning of quantum measurements and the like. What do you think, do these questions still matter today in the era of quantum technologies?
I would think absolutely so. After all, one has to remember that counterfactuality is an idea which was being discussed by professional philosophers long before it was discussed by professional physicists. Counterfactuality is an idea which is just taken for granted, not only in everyday life, but also, for example, in the legal system. I mean, the prosecuting counsel may say to the jury, had the accused not pushed his victim down the stairs, she would still be alive today. That's a typical counterfactual statement. And the jury, in ordinary legal practice, has to decide whether they think that is a true statement or not. And so that problem's been around for many, many years. What quantum mechanics is doing, in a sense, is to enable us to make a more precise and nuanced version of that statement. And for example, there are examples based on the so-called Bell EPR theorem, which enable you to encapsulate that idea of of counterfactuality in rather more technical detail. I've actually discussed that in a recent paper on the subject. So yeah, I think that the question of having to decide exactly what we mean by counterfactuality and whether we could in some sense test it or not is indeed a very fundamental one, and will continue to be with us for many years to come.
So let me ask a very short question. I'm taking this unique opportunity of having you, Tony, and Michel at the same time. So about quantum measurements, about 20 or 30 years ago, you both know Hans Moy from the Netherlands. He was working on superconducting qubits. And I asked him, I was much younger at that time, and I asked him, Hans, how long does it take to make a quantum measurement? And surprisingly, Hans replied, I was expecting a vague answer, but Hans replied, well, I would say around 5 nanoseconds. What do you think about Hans's answer to this question? How long does it take to actually perform a quantum measurement?
Well, I think he was probably thinking of this. Names are floating out of my mind, but there is a technique involving Josephson technology in which you fire a rapid pulse of Josephson radiation into a Josephson something amplifier. I'm sorry, I forget the exact name. But you basically fire a pulse of Josephson radiation into a Josephson system, and depending on the way in which it is reflected or transmitted, you infer certain certain properties of the system, whether it's in state 1 or state 2. And yes, that does take, I think, a matter of a few tenths of nanoseconds, something like that. Yeah.
Yes,
So,
I can actually bring a
yes.
very quantitative answer. So with the superconducting qubits of the transmon type, we now can perform a measurement that will have a 0.1% infidelity, because the time depends on the infidelity that you want to reach. So if you take as a goal to have only a 0.1% infidelity, so that you will discriminate, let's say, the ground state or the excited state with an error that's only 0.1%, you can do this now in 50 nanoseconds. Of course, if you wanted, if you would allow a greater infidelity, you could do it in a shorter time. But let's say we consider that this 0.1% infidelity is what you need for quantum error correction, a healthy quantum error correction. So you have this 50 nanosecond. Other than that, we did measurements of quantum jumps, and in this case, the jumps were much slower. They took about a few microseconds, and we were able to actually stop the quantum jump in the middle and reverse it. So we can now dissect measurement. Not only we can actually resolve their time very, very precisely, but we can stop the measurement in the middle and actually reverse it. So these quantum measurements have become a very precise science, I would say.
Yes, indeed.
Tony, I'm Dino.
Yes.
Hi. Please, I want to ask you what's your idea from theoretical point of view to improve the performance of quantum computers. What aspects of macroscopic quantum mechanics is still need to be explored more in deep?
Okay, I would say
to improve the performance of quantum computers under theoretical point of view, what aspects still need to be explored more in deep, in your opinion?
okay, I think that does depend on whether we assume that as we go to more and more complicated circuits, the general formalism of quantum mechanics and the Born rule and so forth is going to continue to actually work in practice, that is to agree with experiment. If the answer is yes, then I think the main task which needs to be, or the main aspect which needs to be improved, is the generalization of the theory of dissipation in quantum mechanics to environments which are too complicated to be described by the simple Feynman-Vernon, sometimes also called Caldera-Leggett model of these systems. That's, I think, a very important technical point, which has not really got all the attention that it deserves to in the literature of the last 40 years or so. There are one or two papers, for example, by my former student Philip Stamp, which do explore the consequences of modelling one's environment by something more complicated than the standard Feynman-Vernon model. And these sometimes do, apparently, in theory at least, give predictions for the results of dissipation which are different from and sometimes more complicated than those of the ordinary Feynman-Vernon model. That, I think, is probably the most important technical task. If, on the other hand, we assume that that the standard prescriptions based on the Born rule may fail, then, of course, it becomes extremely important to figure out under what circumstances and what conditions this failure may occur. And for example, the recent experiment of Michel and his collaborators are extremely significant in that respect.
Okay, thank you.
Organizzatori nel ringraziare doppiamente Tony Leggett, che nonostante l'età aveva qualche acciacco ieri, però è stato rigorosamente al suo posto, ci ha rilasciato questa deliziosa intervista, insomma veramente merita un applauso doppio, guardate. Non solo un pioniere, ma una persona di grandissimo valore. Allora, il secondo speaker che abbiamo, che avete già intravisto perché ha risposto a una domanda, è Michel Devoret, che ha preso il Premio Nobel poche settimane fa. È considerato un pioniere nell'elettronica quantistica e circuiti quantistici superconduttivi. È proprio la tecnologia di cui stiamo parlando per alcuni computer quantistici, fra cui quello napoletano di cui abbiamo sentito parlare, di cui tutti avete sentito parlare negli ultimi anni, diciamo quello del gruppo coordinato da Francesco Tafuri. Questa tecnologia è possibile grazie al lavoro, alle idee di Tony Leggett e al lavoro pionieristico di Michel Devoret, fra gli altri, che ha preso il premio Nobel proprio su quella tecnologia che poi ha consentito di fare i qubit a superconduttori nelle sue varie declinazioni, perché ce ne sono di vari tipi. Allora, ieri Michel ci ha rilasciato un'intervista, è stato molto simpatico, ne trasmetteremo una breve parte, perché poi dovremo con grande piacere dare la parola a Giorgio Parisi. Allora, non so se siete pronti con Michel Devoret.
that you are just now giving a brief message for the meeting, Timeless Entanglement. So I wish to let you free to express whatever you want, imagining a wide audience in front of you.
Well, I would like in this short message to send all my best wishes to the participants of this event and at Pompei, and look forward to see the beautiful Bay of Naples on some other occasion. I've always very much enjoyed visiting my colleagues in Naples. This dates back from the time where Antonio Barone organized the first MQC conference.
Okay, thank you very much. And there are now a few questions, and there is a question from Dino Ruggero. Please, Dino.
Hi, Michel. I remember very beautiful days during MQC workshops and scientific discussions. Okay, First of all, how are you feeling in these days after the Nobel announcement? And was it something you were somehow expecting, or did it come as a surprise? Please.
Well, yes, it was a total surprise. You are transported all of a sudden in the parallel universe of pop culture person, and so yes, it is a big surprise and something that changes your life all of a sudden.
If you had to explain in a few sentences what your specific contribution has been in the long history from the 80s until now, what would you say?
Well, this experiment was motivated by the question posed by Tony Leggett, do macroscopic variables obey quantum mechanics? This question was linked to the theory of measurements. If, of course, we had brought a solution in the form that macroscopic variables do not obey quantum mechanics, then I think, of course, we would have solved this problem of measurement, but the experiment that John Clark, John Martinez, and I did found that the answer was no. Was yes. Macroscopic variables obey quantum mechanics, and well, I think my main contribution after this experiment has been to recognize that this yes meant that we could build artificial atoms. So these are atoms that you can engineer and to which you can connect wires, so these wires allow you to couple strongly to the atoms or make the atoms couple strongly with each other, which is important for quantum operation. I would say also that with the help of many very talented colleagues all over the world, we have been making these atoms more and more perfect. One sign of progress is the 6 orders of magnitude in their quality factor. Now the transmon artificial atom reaches the quality of the hydrogen atom, a textbook atom. So this is quite spectacular. And I would say that artificial atom physics, artificial atomic physics can do experiments that are very difficult or even simply impossible in natural atomic physics.
Hi, Michel. I have a question. If you go back in the 80s when you were doing the experiment, which was the hardest part of the experiment, the challenge,
Well, the challenge in this experiment was to be able to communicate with a Josephson junction, which was a macroscopic quantum system, but at the same time to protect from all the spurious noises. So we had to engineer a very narrow bandwidth, a channel with which we would communicate with this macroscopic quantum system, but at the same time protected from the influence of the environment. So the problem is it's a Trojan horse problem. You want to get measurement out of the system, but you have to prevent any back action from the measurement system. So this was the challenge at the time. It remains the challenge today, but we have now many more techniques at our disposal.
So was it simpler to measure those junctions or nowadays a transmon?
No, I would not say that it's simpler. It's just that we have learned the technique so we can use ready-made instruments if you want. We don't have to rebuild everything from scratch and understand all the conditions from scratch. The field, as if you want, is more engineering now than this question of access has evolved in the sense that the solutions are more standardized. It's like it's exactly like other domains of physics, like atomic physics or quantum optics, which now have powerful lasers, very very well controlled lasers, whereas in the 60s people had to build pretty much their own lasers.
Yeah.
Bene, grazie mille. Dovrebbe esserci in linea